So welcome. Sorry for the delay. And we're going to start our PhD 3-minute pitch session. We have 8 PhD students to get through, and we will start with Alex Pierron from Télécom SudParis.
Thanks. So my PhD is about cybersecurity impact of AI optimization techniques in B5G networks. I'm supervised by Joaquin Garcia Alfaro, José Rubianan, Michel Barbeau, and Luca De Cinco. And this PhD is part of the PEPR Future Networks and is funded by it. So what is the topic of the PhD? It focuses on reinforcement learning and its risk while operating risk. What is a risk? It's this thing. It's a tunable mirror that you can use in order to reflect a signal. So what's the use of it? It's very useful to deal with obstacles when usually you would use another antenna. Now we can deploy a RIS and use it to send the signal to your users. And we want to manipulate it with reinforcement learning because it's a very hard problem, nonlinear and very hard to solve. And that's where reinforcement learning is taking an edge. The advantages of RIS is that they are very low in consumption and so on. So there is also economical values to that. And we want to see what are the issues of reinforcement learning on the security of the system. So this is the very big picture, another scheme. So you've got the base station that sends the signal to the RIS, and then that sends to our users and the bad guys, the red team, I would say, just the red team that wants to make attacks. And we want to study how the RIS operated by reinforcement learning can be attacked. It can also defend itself. So a quick word about the reinforcement learning approach we have. We have several algorithms that we use, we will use, TDPG, TD3 SAC. It's a bit of name dropping for the guys that are interested in this topic. And also for the attacking team, we consider using multi-agent reinforcement learning so that we can have some very insightful, maybe attack schemes that can be here. So this is for the high-level roadmap. I need to develop the environment, the simulation environment, and also demonstrate proof of attack using reinforcement learning in the flows identified, then analyze, enhance the tools, and also validate maybe on real test beds. Since it's a part of the PEPR, as I mentioned before. So this is the ongoing work this time, what I'm doing currently day to day. We are working on fairness issues because we have identified in the literature that we have a very strong issue of fairness of just sending the signal to the different users in a fair way. So that's what we are trying to investigate and correct. And it has led to a submission. We'll see if it's accepted. So if you have any other question or any inquiries about my research, feel free to join me at the poster session so we can discuss it. Thanks.
Perfect. Next up is Tiphaine Georges from Télécom Paris.
Hi everyone. So I'm a PhD student between Orange and Télécom Paris. And I'm working on the modeling, the mathematic modeling of the circular economy of a smartphone. So we will define briefly the subject. So circular economy, what we mean by circular economy is the refurbishment and recycling of smartphone. And it is put in place in the aim of reducing the use of resources and pollution. Telecom operators use buyback prices to incentivize refurbishment to be able to collect smartphones. But buyback also have drawbacks and encourage customers to reduce their lifespan of the lifespan of their phones. So the problem is it results in an increase in consumption. And we want to see if this rebound effect run counter to the environmental objective. So this is the model we introduced 2 types of smartphones, basic and premium. The premium phones can be refurbished, and the basic one are cheaper but cannot be refurbished. And one of the main aspects of the model is that if a refurbished customers can't buy a smartphone because there are not enough refurbished product on the market, they buy a basic phone instead. And so we wanted to see the evolution of pollution and other economic, other environmental indicators with buyback prices. So these are the results we obtain with this model. And so we can see that pollution, waste, decrease and increase with buyback and reach a minimum for non-negative buyback prices. And it means that we can reach a minimum of pollution with in this system. And it is a very good news. And the average lifespan of product is also maximized for the particular buyback prices. And the main result of my thesis for the moment is that this optimal buyback prices is the equality between supply and demand on the refurbished market. And it's mean that as long as we can serve more refurbished customers, it is beneficial to increase the buyback prices. So don't hesitate to ask if you have any question. But thank you.
Yeah, we don't have time for questions, but reach out to the PhDs later. Yes, no problem. Next up is Aoyu from Nokia Bell Labs. Get out of my way. Nope, it's all good.
Okay. Hello everyone. My name is Aoyu in Chinese pronunciation. Okay. Today my topic is V2X enabled air-ground traffic coordination for enhancing on-demand air taxi mobility. Okay. Urban air mobility or UAM offers a promising solution to urban coordination by extending transportation into the low-altitude airspace. But how to integrate UAM with ground transport system remains challenging. What part is eVTOL used to take off and land? Okay, the what part capacity limits and the multimodal coordination complexity. So our work is to optimize what part selection and enable real-time air-ground coordination for efficient door-to-door air taxi service. Okay, there are three challenges. The first is how to gather and combine different types of real-time information, include the ground transportation information, the airspace, and the passenger requirements. And the second is how to model the whole deal for the whole process for the passengers from the passengers organization to their destination. There are different processes. Include the ground travel, the vertical waiting, and so on. And the second is how to balancing resources across ground and air. So we propose a UAGMC, Unified Air-Ground Mobility Coordination Optimization Framework that we get the passenger requirements, the ground information, the air information, and the vertical information from the environment. They are multi-source, so they have different tabs. And we use multi-source contextual embedding to process this multi-source data into a feature vector. Okay, and we use spatial temperature integration network. This block we use is LCATM to process this future vector and to process some time future. Okay, and we use reinforcement decision making is actual critic algorithm PPO. Okay, through these two blocks we proposed that it can process this multi-source state easily and choose the which port for the passages. Okay, we do so many experiments to with other baselines against with other baseline algorithm. It show me our algorithm UHMC can reduce the passengers travel time. The ATT's average travel time for all passengers. Okay, we also do some solution experiments that shows the two blocks for our purpose is useful. Okay. In conclusion, is that we formulating a door-to-door taxi routine as a market distinction precise. And the second is that it was UHMC. Okay, if you want to know more details, you can ask me at the poster session. Okay, thank you all.
Next up is Julien Cardinal from Inria. Sorry, I have to move.
Hello, everybody. I'm Julien Cardinal, and I'm working under the supervision of Anna Buzic on min-field control for demand-side management. So first of all, what is demand-side management? It's the act of controlling the demand according to adapt it to the supply at all time. And we apply our algorithms to thermostatically controlled loads, which are electrical systems that aims at keeping their temperature within a specified range. So I be applying the algorithm to water heaters, and yesterday Tomas presented his work on electrical vehicles. So we are in the setting of a distributed load problem, where we take into account into input a target consumption, and our algorithm predicts a policy that we give to every electrical systems, and we at the end we get back the average consumption, and we want in the tracking setting to have this average consumption as close as possible to the target consumption. And in the consumption cap setting, to have this average consumption always lower than a maximal consumption. So for the water heater, we model it with a differential equation that takes into account the heat loss by the isolation of the water heater, the Joule effect when we heat up the water, and the water drain whenever the user takes some water, we need to replace it with cold water. So the typical cycle of the water heaters, called nominal trajectory, is as follows. The water heaters keeps being turned off until it reaches the minimal temperature, and then turns on until it reaches the maximal temperature, and on and on. And to that, we add two controlled switches. And this is a way to move the consumption of the water heater to early in the day, or to push it back to late in the evening. And to apply our algorithm, we make the mean field assumptions. So we consider our water heaters to be homogeneous, and that we have a large amount of water heaters. And here are our results. For the tracking problem, we have a solution that tracks the red curve correctly. But when we apply it to the test set, we are good in the short term, but not in the long term. So we need to we apply MPC and relearn every 10 minutes to better fit the curve. Here are other constraints. Thank you for your attention.
Perfect. Next up is Luis Muñecas Tomas.
Hello, everyone. I'm Luis, first year PhD student between Nokia and Inria. And my topic is about certification of quantum systems in quantum networks. So I'm going to explain to you, first of all, like my problem falls into the paradigm of distributed quantum computing, where you have several quantum processors interacting between each other and hopefully trying to solve a certain task beyond what we are capable of doing with classical networks. And so we have the quantum networks that's going to be responsible for distributing the entanglement, which is the resource that will enable essentially the quantum applications. And what we want also is certificating that the network is doing what it's doing and it's having the states that we have and that we want. And for that, we have the tool of self-testing. So I'm gonna try to give a little explanation of how it works. So we want to assume we have two nodes. We of course call them Alice and Bob, and we treat them. We don't want to assume anything about the nodes or the internal workings. So we just treat them as black boxes, where we have some input and some outputs, and so there's a state that's unknown for now, and that we want to extract some properties. And so in the end of this experiment, we repeat it several times, and we have some correlations, some probabilities of the outputs given the inputs. And only from these correlations, we are able to use certain tool that's called a Bell inequality. And from there, if this inequality is violated, we are able to infer properties about the state that is shared between the nodes, and also the operations that are done in the nodes of the network. And then we also we are interested in applying these tools for distributed problems such as Byzantine agreement, where basically it's a distributed computing problem where we want to achieve consensus between the network, and we are able to see, for instance, that we have impossibility results of consensus in the number of nodes if we don't modify the problem. We have a bound of a third of the nodes that have to be truthful or not working badly. And we are interested in seeing if we are able to find any quantum advantage even if we modify the problem a little bit, or if we are able to see an advantage in the number of rounds that is allowed to solve the problem. And yeah, I'm happy to discuss in the poster session. Thank you very much.
Thank you. Next up is Iain Burges.
Hello. Okay, so hi, I'm Iain. It's kind of hard to see the board from here, but I'm working in quantum computing and some general security stuff related to that. Today, I'm going to be talking a little bit about reinforcement learning in this context. My advisors are Joaquin and Michel, and yeah, we'll get right into it. So to start with, quantum computing can give you a lot of very interesting advantages. For example, you can actually invert a matrix exponentially faster than you can with a classical computer. The problem is you can only do this in very, very special circumstances. And these circumstances might exclusively be useless circumstances. So that's a bit of an issue. And it's often proposed that we could use this in the context of supervised and unsupervised quantum machine learning. But these two things don't generally satisfy the constraints that we need, where we need a very well-behaved matrix, and yeah, it's just not necessarily very reasonable or feasible in a lot of contexts, which is too bad. And then there's the other problem of, okay, we get an exponential improvement, but if we have to load the same amount of data in as before, that kind of cuts into all of the improvements we have. So maybe quantum isn't exactly worth it. However, we might be able to leverage reinforcement learning because that's less about loading in pre-existing data and a lot more about representing an environment and learning how to better act within that environment, which you can simulate a lot easier. So quantum computers are really, really great at dealing with high-dimensional, well-structured spaces. Adversarial games happen to satisfy both of those problems. So you can represent things that are very well behaved and very well structured. So in this case, we have a little cat and mouse. And the nice thing about adversarial games is also they cover most problems in security, but wherever else, there's a lot of general applications. So the solution that I'm proposing, and which is going to take a lot of math to figure out, and we'll see if we can make it work, is we take a quantum support vector machine. It pretty much takes advantage of the matrix inversion algorithm to separate between different states. You use that to pick actions, and then you iteratively make a better and better quantum support vector machine using tools from reinforcement learning. So that's the main idea. Thank you.
Perfect. Next up is Hugo Rimlinger from Sorbonne Université.
Hi everyone. So I'm a second-year PhD student under the supervision of Timo Friedman, Olivier Fourmeau, and Kevin Vermeulen. I've been mostly working on two main projects so far. For those who may remember, I presented the first one last year at the workshop on the topic of internet scale IP address geolocation. This was accepted at Connext 2025. I'll be presenting that next December. And we currently hold the largest publicly available data set of IP address geolocation. And currently, I'm working on the project of BGP hijacks at internet exchange points. So BGP, very briefly, we have an AS. So BGP is the unique protocol for exchanging data between autonomous systems. So we have an autonomous system V that wants to share its prefixes to the rest of the internet. It will announce the route to its provider, here too, and then the route is propagated through the internet until every ASs know how to reach those prefixes. So what's the problem? Well, BGP in its introduction in 1985 wasn't built with security in mind, and more specifically, there exists no sufficient authentication mechanism to prevent a malicious ASs to announce a prefix that it doesn't own, which is called a BGP hijack. Because of this lack of authentication mechanism, research has been focusing on detecting those hijacks to mitigate them. We have basically two families of detection system: data plane, which uses ping and trace route to detect hijack, and control plane, which analyze publicly available BGP updates to detect the occurrence of a hijack. We started with this project with a definition of shadow areas which are part of the network where we could perform a BGP hijack while not being detected. These shadow areas relies on two criteria. Our updates avoid BGP monitoring to avoid control plane detection. And then we want to be able to forward the captured traffic back to the victim in a man-in-the-middle fashion to avoid data plane. And we focused this study on internet exchange points, which are large switch fabrics that is the interconnection of ASs. This allows us to have a large surface of attack, and this hasn't been quite covered in the current literature. Very briefly, the threat model we have in mind, the same topology, but then now we have an attacker, A, peering at an IXP, which announced the route of the victim to peer 5. And because of the value-free rule, which is a specificity of BGP, the route is only propagated to the client of 5. And we can very much easily check that those ASs do not have BGP monitoring, and we still have a route back to the victim. And so, yeah, the goal is to focus on real-world experiments and to use IXP's properties to perform those stealth BGP hijacks. Thank you very much.
And to finish off, we have Shu Li from Inria.
Hello, everyone. It's my honor to introduce my new job work with my supervisor, Anna Bucici, Rimlinger, and Luan. So acoustic matching model is consists of matching graph, matching place, and the arrival probability. The items one by one commit the system. If they can consider of an age, they are matched and left the system. If not, they have to save in the system. And the expression of the numbers is the performance. If the system is more ages, have a bigger performance. It's called the products. In 2021, these scholars give the stationary distribution about on the simple graph and multiple graphs. In 2022, these scholars give the formula on the simple graphs. In this work, we give the expression formula on the multiple graphs. Let's be a multiple graph, and the nodes divided in two parts. The first one is every node with a simple graph, and the check G is the G, deleting the all the self loops, and the I is the independent. G is the intersection of the independent and V2. Then we give the expression formula, is which is product form. Based on this theorem, we make a simulation, and here. I give two simple example. The more details are the post. Thank you.